All right, I guess we'll get started. So, hi everybody. For those of you who don't know me, my name is Jake. I'm one of the co-organizers of the Desert Data Science User Group here hosted at Udestic. How many of you guys, I always like to do this just like a show of hands, but how many of you guys are coming here for the first time? It's your first meeting. Nice, lovely faces. Thanks for coming down and trying us out. Hopefully you enjoy yourselves. How many of you are here returning members coming to the second run? Right on, welcome back. Thanks for coming back, guys. Really appreciate that influx of people coming back. It's what helps us stay alive. Just a couple announcements before we get started. Wi-Fi, if you need to connect your laptop, mobile device, whatever, to the network. Guest network and password are right there, so feel free to go up and read that and type it into whatever you type it into at any times. I tried to send a couple of announcements, but just to make sure everyone's on the same page. We no longer validate parking for that garage across the street, so if you did park there and got a ticket, I highly suggest you move it now, so that way you have to pay less than you have to. If you are commuting by car here, there are plenty of meters out right in front of the garage that you can park at. Those are free after 6, which is 2 minutes ago. So you should be fine if you park there. So just a reminder if anyone needs to move their car to do so. If you're at these meters, then you can pick up. I would like to open it up to any announcements that anyone wants to make about other presentations that they're doing, any projects that they're working on, any positions that they're looking to hire people on, anything of that nature. I know Connie has SQL Saturday, so I'll go ahead and let her go first to do her first spiel.
Hi, I'm for the local SQL Saturday SQL Server user group. And we've been in training event called SQL Saturday. It's sponsored by Microsoft. We have people from around the world actually present. It's a 3-day training. We ask for you to take your lesson. There are 8 different tracks. There's VBA, there's Power AI, there are apps, there's professional development, Azure, for the information online, and the actually and people work at transportation colleges.
Right on, thank you. SQL Saturday, April 4th at Grand Canyon University? Yeah, GCU. Awesome, cool. Anybody else, anything that they want to make an announcement of? We'll open it up again at the end, so if you have something you forgot about it, feel free to bring it up at the end. But if anyone else has anything, cool. Then we're going to go ahead and open it up to Bindya, so go ahead and kick it off for her. She's a PhD student over at ASU, presenting some of her research. So without further ado, Bindya, take it. Thank you.
Hi everyone, thank you so much for coming today, and thank you so much for the opportunity. And I'm here today to present my PhD, one of my PhD project, which is on uncertainty quantification in deep learning. And this is going to be today's agenda. I'll start off by briefly telling or motivating why we need to worry about quantifying uncertainties in deep predictive models, and then talk about different types of uncertainties in these models and the existing strategies, and a brief intro about some of the strategies that we proposed. And so we all know deep predictive models or deep learning models have been used right from everyday applications like voice assistants or autonomous systems to even coming up with hypotheses of how things work. So right from healthcare, robotics, medicine, object tracking, so all these are some of the fields in which deep learning models have been exponentially used. And the reason for this exponential growth of application of these models could be the availability of more data and computational resources. So even though these deep predictive models are given performances which are superior to humans, there are some challenges that needs to be addressed. So before that, this was a recent tweet by Jeffrey Hinton. So he starts by questioning if you have 2 options. One is a black box AI surgeon, which cannot he calls it black box because it cannot explain how it's working. And suppose it gives you a 90% cure rate, and a human surgeon who can explain what's happening and why a human surgeon takes certain decision, but gives you only 80% cure rate. what would your option? What would you select, or do you consider the AI surgeon in this case to be illegal? Like, anyone wants to answer this question or tell your opinion about it?
I don't know if there's legality that you can express, but I think it's personal. I go with 80%.
Personally, even though I'm doing my research in this area, I could go with 80%. That's the human surgeon. The two things to focus here is, first of all, these are black box models. So we don't know what's happening, what the model has learned, why is it predicting something, or why is it not predicting something. So there are several questions that needs to be answered. And the other thing is, it says 90% cure. So it's just an aggregate metric. So given a certain population, we don't know if the deep models are performing well on critical examples or rare examples. So we have no idea about it. We just have an aggregate accuracy metric and just say 90%. So the model might be doing well on all easy samples and might be missing tough examples or rare examples. So these are some of the challenges that we face while implementing data-driven machine learning models and specific deep learning models. So in the future slides, I'll be talking in depth about all these points, but in brief, so since these are data-driven models, the main component is data, of course. So you need to have good quality data. And the other important question is how much and when can you trust these models? And there's been a lot of work showing that these models are vulnerable and don't generalize well. And again, there's interpretability and explainability issues. So we don't know what's happening or what the model is learning. So the first challenge being data, as we all know, the core ingredient is data, and we need lots of data to train such models. But availability of data in certain scientific fields might be difficult, or even to collect such data might take a long time. So there's those issues. The other issue is annotating cost. So it might be difficult to have a human to label all the examples. So, and the next challenge is the quality. What if your data itself is noisy and you train a model and end up with inaccurate estimates? And again, the collection environment, the data collection environment is stochastic. The real world being uncertain, random or uncertain. What happens is the time during which you collect the data the conditions during which you collect the data might be completely different from when you deploy the models. And again, the diversity. So in this example, if you see, in case, suppose we say we train a model based on dog versus cat classification model. It's a toy example, but just say you use all dog pictures that are white and cats that are black, and you try to test the model with a black dog picture. We don't know if the model is going to correctly predict it, because we don't know if the model is learn the classification based on the color of the picture, or we don't know which feature contributed to the model training. So these are some issues with the data. So the other important issue is bias and reliability. So these were some of the problems that we saw by using AI models. So in the first example, the model was biased. There was a racial bias. And in the second example also it was the same. The model was biased towards people who were white and not black. And the last example was the self-driving car incident that happened in Arizona that killed a woman, where the model failed to recognize the pedestrian. And this is again another issue, reliability. So the questions of, suppose to deploy these models in healthcare, we need to collect large amounts of data from the humans, and all these will give rise to ethical questions of whether you can share personal health information with such models. So this was another case where there was racial bias, where people have started using AI models to automate decision-making process in case of um, criminal justice and things. So the important questions in such cases would be like, when you trust these models, we have no information. So again, how much do you trust? And when should a human intervene in the process so that the decision-making process can be more reliable? So this is the next challenge. So vulnerability. There are several literature that shows the deep learning models to be moved easily. So in the first example, this is an healthcare example where images with small addition of noise are classified wrongly. For instance, in the first case, it's the no diabetic retinopathy case, but just a small perturbation or noise will result in misclassification, which is very problematic in critical applications. And in the second example, it's the same thing. So the panda was misclassified just by adding some small amount of noise. The other issue is generalizability. Suppose you say you train your model on cats and dog images, but what if your model is given another input, say a turtle image? So in this case, I wouldn't want my model to predict this as a cat with 80% confidence. So I would rather have my model predict something like that, like 40 and 50%. So in that case, the human can make a decision saying the model is not confident, and the human can take over the decision-making process. And again, as I said, these are black box models, and explaining what's happening and what the model is learning is complex. And given several factors, we are not sure how the model, the data, and the learning strategies interact with each other. So the next issue is interpretability and explainability. In this work, it was shown that a simple perturbation to the image was led to misclassification. So we don't know what features the model is using to predict the second image's dumbbell versus first image's stop or incorrectly. And in the third case, it's again a misclassification. We don't know which feature is causing that, and we have no control over it. And the other reason is everything is stochastic. So the time when you train the model doesn't have to be same as when you deploy these models. So there are a wide variety of sources that contribute to all these kind of uncertainties or randomness in these models. One being the non-stationarities or the assumptions that we make about the environment and the priors that we place while building these models, and the way we sample the training data itself. The other thing is the learning strategy, whether we use a complex learning strategy or a simple strategy, and the approximations and assumptions that we make throughout the learning process. So given all these issues or challenges, one way to overcome this is by quantifying uncertainties. So when you have a model and you don't know if you can allow the model to express its ambiguities, so that can be done through uncertainty. So a model can be made to learn not only to predict something, but also to express its uncertainties. So for instance, in case of classification, the model can come up with uncertainty estimates or variance estimates. So whenever it's not sure about some prediction, it can just give a high uncertainty value. So basically, uncertainty quantification is a statistical field of study where it allows the model to accurately express what it's learning, and whenever the model is not sure, it can just throw some uncertainty estimates to the user. And instead of having deterministic models, uncertainty quantification allows us to have probabilistic models. So instead of just giving point estimates, we actually output distributions. So that way, there is some sort of uncertainty information given to the user. So again, as I said, to overcome all these challenges, we can use or we can incorporate uncertainty quantification in our modeling. So the first aspect, why do we need to even bother about uncertainty quantification with respect to modeling perspective is, so we don't want machines that are overly confident while making mistakes. It's okay to have a machine which has a lower accuracy, but it has to be confident about its predictions. So it's fine to have a model with, say, 85% accuracy than to have a model which is 90% accurate, but being overly confident even when it's making mistakes. So in the previous example, in the turtle example, in the first case, if you see the model is overconfident, but it's saying it's 80% cat. So in such cases, we would rather have a model which is not very confident about its prediction with lower accuracy. Again, having good uncertainty estimates will allow human to come into the decision-making process and to identify where the model is weak and strong, so that extra training can be incorporated or the data collection process can be made better. And in critical applications like healthcare, medicine, autonomous driving, we would prefer having reliable models because it's a question of life. And again,
are you talking about just single models or these collaborative models that are working together?
So in case of uncertainty estimates, there are some techniques where statistical prior and statistical techniques can be incorporated just within a single model to come up with these kind of randomness or some uncertainty estimates, but there are techniques where you can use multiple models and come up with uncertainty estimates. Yeah, I'll be talking about it. And again, to have some knowledge, suppose we have some knowledge, prior knowledge about an application, we can incorporate those priors while building the models to uncertainty quantification strategies. So with the deployment perspective, we would prefer to have models that are valid, reliable, safe, which are fair and not biased towards any features. Again, we want them to be explainable, and some applications like reinforcement learning, etc., would require uncertainty quantification, uncertainty estimates. So, yeah. So, in specific and deep learning models, there are two kinds of uncertainty estimates or uncertainties, and mainly two types. So, in the first type, which is called the aleatoric or intrinsic uncertainties, so it's actually due to the measurement noise. So the way we collect the data, the noise in the data process, or the assumptions that we make while collecting the data contributes to the aleatoric uncertainties. So since it's inherent uncertainties, we have no control over it, and collecting more data or more training data will not allow the model to be any better. These uncertainties won't reduce. The other class of uncertainties is the epistemic or Bayesian uncertainties. So this can be due to our simplification assumptions on the data modeling. So for instance, using inefficient models. So if the data is too complex, but you end up using a simple model. So in that case, you will end up with errors or uncertainties. And even when you have limited data, suppose the data is not well sampled in real situation, so that contributes to epistemic uncertainties. And again, since it's due to limited learning or assumptions that we make, it can be reduced through collecting more data or using better models to fit our data. And the last class of uncertainties in deep learning models is the approximation and optimization of uncertainties, which is usually ignored. I mean, they're not significant when compared to aleatoric and epistemic uncertainties, so they're usually ignored. So in this image, if you see the crosses represents the data, sample data, and the red curve represents the true data or the target that we need to predict, the target data, sorry. And so the aleatoric uncertainty, which is the uncertainty in the data sampling or the inherent uncertainty in the data itself, is represented by the blue curve there. So it's basically how I sample, and so we want the actual data to follow the red curve, but since due to the noise in the collection process, it leads to some aleatoric uncertainties, and the epistemic uncertainties corresponds to where we have no knowledge about the data itself, or the model is not seeing such data, or the data region is not well sampled. Again, aleatoric uncertainties cannot be reduced because we have no control over it, but epistemic can be reduced by sampling more in those regions. So the next question is, how do we quantify these uncertainties? One way is to use black box estimators. So without differentiating the uncertainty sources, like without saying whether the uncertainty or the error in the learning process is due to the data or due to the modeling process, you can use black box estimation techniques. The other is the gray box estimation techniques. In some applications, if you have a good knowledge that the data that you've collected is very good and the errors are mostly due to the models. So in such cases, we can resort to gray box estimators. I'll be giving some examples about these two in the future slides. And the other way to categorize these uncertainty quantification strategies would be whether we take a Bayesian route or the approximate techniques like frequent approaches to estimate uncertainties. So I'll be briefly talking about existing strategies in the future slides. So before we move forward to the exact techniques like Bayesian neural nets, we can actually look at the neural net model itself as in terms of a probabilistic view. So say in case we have the training data X, that's the input features, and the target data, that's Y, and you have a model F, which is parameterized with W's. So there are some weights to your neural network that's represented by W. So we come up with a model F such that giving the input X, you will get the predicted or the target Y. So we place some prior on the weights. So it can be as simple as just some initializations on the weight matrix. So it's just some prior. In some applications, we might have some knowledge that can be embedded in those priors, but we can just start with a random prior too. And then we actually compute the update the weights that we have initialized by computing the likelihood. So since we have the actual target and the input features that corresponds to that target, we try to use the base rule, which is the likelihood multiplied with the prior here. So by computing the base rule there, we update the prior knowledge that we place on the network parameters. And then inferences, when you get new data X star, you try to predict what Y star is. So the issue with all these Bayesian kind of techniques is if you have large amounts of data, fitting Bayesian models, putting prior distributions, or computing these integrals is not easy. So that's one issue. The other issue is again having large models and placing priors on large models and performing base rule updates is never easy. So, there have been approximations in the literature that show Bayesian neural nets can be implemented. So in Bayesian neural nets, what actually happens is the weights, for instance, if you see in the first figure, the weights are just single scalar values. So these are actually replaced with distributions. So it can be as simple as just placing Gaussian distributions on each weight parameter. Excuse me. Weight parameter. So whenever you do some prediction with this model, it's just not with single scalar values or deterministic weight values. It's with the distribution. So you have some sort of uncertainty already embedded in your model priors. So in case of Gaussians, since they are defined completely with the mean and the variance there is giving you some notion of uncertainties. Again, to implement these integrals, there is techniques like variation, inference, and sampling techniques that has been proposed. I'm not going to talk much about that. And so Bayesian neural nets, since we place distributions on weight parameters, so it's basically used to measure the epistemic uncertainties, which corresponds to the model uncertainties. So we have some randomness already introduced in the model. So basically, when you do a random trial from these distributions, there is some notion of perturbation every time you do this. So some sort of uncertainties can be captured, and since it's basically on the model and nothing on the data, we call this. I mean, we use these to estimate the epistemic uncertainties. The next class of uncertainty estimation techniques is the Monte Carlo dropout technique. So this is an approximate estimation technique, and this is again used to estimate model uncertainties or epistemic uncertainties. So what people do here is, so randomly the neurons are dropped from the model. So this way there is some randomness again introduced in the model. And usually it was used to use as a regularization technique to avoid codependence, to avoid excessive codependence of neurons with each other. But it has been shown that this kind of an approximation is actually, it can be shown to approximate the Bayesian priors that we placed in the Bayesian neural nets. So basically, what happens is, in dropout, dropout is enabled both during the test and training phases. So in the training phases, it enables generalization performance by acting as a regularizer. But when during the test time, dropping the units randomly will actually bring in some sort of randomness every time. So we do this. We actually pass the test sample xi through the model with dropout probability p. So with the probability of p, we will be dropping units in the layers of the model. And suppose I do 5 passes of my data. So I pass the data xi 5 times through the network, but a dropout being enabled during the test time. So every time I do, I get different predictions. So all 5 times I have different predictions for the same input xi. So the mean of those predictions can be used as my final prediction, and the variance that I get is some sort of uncertainty in the model. Again, this is exactly, I mean, this has been shown to approximate the Bayesian neural net process, but the problem is selecting the right dropout probability is crucial. The other class of techniques is deep ensembles. So again, as you asked about having many models versus just a single model to estimate uncertainties. So in deep ensembles, we have like n number of models, and we try to compare the predictions of all these n models and estimate some sort of variance there. So the basic assumption is not all models make same mistake. So we have n different models. The models are different, meaning the way I build these models can be done through these techniques. Like I can use different training data to train each model. The model architecture can vary, and the way I combine the outputs from all these n number of models can vary. So I'll have like n models, and all n models are slightly different from each other. So whenever I pass the same test input through all these models, I get different predictions every time, and again, the average prediction can be my final prediction, and the variance across all these predictions can correspond to the model uncertainty or epistemic uncertainty. So we spoke about estimating model uncertainties in the previous techniques. One was with Bayesian neural nets, where I place priors or distributions on the weight parameters. And the second one was through dropout, where I randomly drop units while testing. And the third one was deep ensembles, so where I have multiple models and I try to combine the predictions from multiple models. So the next set of estimators is to estimate the alloteric noise or the alloteric uncertainties, which corresponds to the noise in the data. So for the first class of estimation techniques here is the distribution estimation. So basically, if I assume my data is following some distribution, so I try to estimate the parameters of that distribution. So that way I know what how much noise is there in the data, or some information about the data or distribution itself. So for instance, but the basic assumption that we make here is we know what kind of distribution class that the data is sampled from. So for instance, in heteroscedastic neural networks, we assume the output target, that's y, that follows a Gaussian distribution. So in order to define a Gaussian distribution, we just need the variance and the mean. So we come up with a loss function like this, wherein the model is optimized to predict the mu and the sigma. Mu is the mean of the target, and sigma is the variance of the target distribution. And so basically, how the loss function works is whenever my residue, that is yi minus mu, is too high, in order to reduce the whole loss function, the sigma I is small. So it means if the mean that I'm predicting is far away from my true value or the target, I expect higher uncertainties or higher variances. And the second term is just used as a regularizer, such that I don't get large sigma values. So the other uncertainty estimation technique to evaluate, to get some alloteric estimates would be through quantile-based estimations. So what we do here is, in the previous case, we assumed a Gaussian distribution, but in cases where we don't have any prior distribution on the residuals, we can use quantile regression to come up with what is called as prediction uncertainties. So we come up with prediction intervals. Basically, in this figure, if you see, we estimate quantiles corresponding to 0.9 and 0.02. So that way we have some uncertainty bound on my data. So we use a function, a loss function called as a pinball loss. So basically, we can show that it has been shown that by estimating the any two quantiles, we can actually estimate the prediction uncertainty itself. So the interquantile distance between any two quantiles that we consider gives you some notion of uncertainty. For instance, if I consider 0.9 quantile and 0.1 quantile, So we get some uncertainty estimates that are well calibrated for 0.8 confidence interval or 80% confidence interval.
Great question.
Yeah.
So the lower that confidence interval, or I guess the higher that confidence interval, is that the more uncertainty that you have in your model?
Yeah, so for instance, in some applications, you would be more interested to just find out about 95% confidence values, say in finance and such applications. You just worry about 95th or 95th confidence interval. So in such cases, you can just select any two quantile ranges. So, and then the difference between those two quantile ranges will give you the uncertainty informations. So, as I said, for instance, if you consider 0.1 and 0.9, it will give you 80% confidence interval. So, something like that. So, we've seen so many techniques to estimate uncertainties or variances in your prediction process. But the next question is, how do you evaluate these uncertainty estimates? So we don't actually have any ground truth uncertainty. We don't know what the model is learning. We don't know what errors are incorporated in our data or even in our learning procedure. And given the complexity of these models, we don't know how all these factors like data, the learning process, or the assumptions, all these are interacting with each other. So one way to analyze the quality of these uncertainty estimates would be with these scenarios. So in first scenario, when you have unseen data, suppose you've trained a model only with specific data or data sample from a specific region, but you try to predict data from some other distribution or some other space. So in such cases, you expect the model to produce high uncertainties. So if the model is doing that, then the quality of uncertainty estimates can be trusted. So the other way to check the quality of the uncertainty estimates would be when the model is making mistakes. So when the model is classifying something incorrectly, so in such cases, I expect my uncertainty estimates to be high. So, and again, to explain the model behavior. So in the previous example, in one of the examples, in this example, so even though model is, it's misclassifying things, but we would expect if the model is not sure, it can just simply produce high uncertainties rather than just misclassifying it. So if your model uncertainty estimates can explain what your model has learned, then the quality is good. The quality can be considered to be good. So since there are no ground truth uncertainties, evaluating these is really challenging. But in statistics, there's a metric called as calibration that is being used to evaluate all these uncertainty estimation techniques. And it has been shown that all the existing deep learning models are not well calibrated. And also through tasks that rely on uncertainty estimates. So for instance, in reinforcement learning, if you actually need some uncertainty estimates to take the next decision. So if the uncertainty estimates are helping your decision-making process, then you can consider them to be good. So I would like to elaborate a little bit on calibration because that's the only metric that's mostly being used to evaluate any uncertainty estimation strategy. So mainly I'll be talking about classification and regression tasks and explaining what calibration means. So in case of classification problem, calibration can be defined as the extent to which your prediction probabilities and the true likelihood are consistent. So we saw some toy examples before. So if the model is predicting something correctly, we would like it to have higher confidence, versus when it's predicting incorrectly, it should have lower confidence. So again, same example. In the second case, if you see the model is misclassifying, but it's again overconfident. It's 80%, 85% CAD, which is not desirable. In such cases, the calibration of these probabilities will be poor. So in the third case, you see the calibration for predictions where it's predicting 45% that it's a dog and 55% it's a cat. It's said to be well calibrated, but unlike the first case where the uncertainty estimates are not calibrated well. So in regression problems, uncertainty estimates are through prediction intervals. So suppose you have a prediction interval y minus delta and y plus delta, where y plus delta is the upper range of my prediction interval and the lower range, and y hat represents my predicted value. So we say these kind of intervals are well calibrated if the probability of my true value or the true target, that's y, is say for we predict an interval for 80%, like using quantile regression or something, and we expect 80% of the true values to lie within the intervals that are produced. So in those cases, my model is said to be well calibrated. So this expression precisely tells that. So the probability of my lower interval less than my true value less than higher interval should be consistent with the alpha, which is my confidence value of the considered interval.
Is the calibration metric, is it dependent on the model performance like the accuracy of your?
Yeah, it is dependent on model accuracy as well, because y-hat is taken into consideration while predicting intervals. So it's just not, I can randomly produce a large width and say it's well calibrated. For instance, say I produce like infinitely large bands for my prediction intervals and calculate how many true values lie within it. So it can be 100%, but in that case, it's not meaningful. But through this definition, we are actually considering the mean of the prediction or the prediction value itself. So this is just an illustration of well-calibrated and uncalibrated intervals. So in this first figure, which is a 70% confidence interval, we expect around 70% of the points to lie within the confidence bounds that we predict, which is the shaded area, versus a calibrated interval in which we can expect about 70% of the true values lying in the intervals that we produce. So in applications like time series forecasting, so we'll have to we just don't want to just predict something about the future, but we in case we can provide these confidence bounds, then if the estimates are not accurate enough, some measure can be taken to even retrain the model or to collect more data, etc. And again, we avoid large bounds there. So now I'll be talking about some of the proposed strategies. So in the first technique, we actually try to come up with regression models that are very calibrated. So a lot of literature has been done on calibrating classification models. There's models like temperature scaling, where the output probabilities are output softmax probabilities are adjusted, and there are other billing kind of strategies for calibrating classification models. But not much work is being done on regression models. So in this strategy, what we do is we actually pose the problem of. So as I told earlier, in regression problems, in addition to having a mean estimate, we also have uncertainties in the form of prediction intervals or confidence bounds. So we pose this problem of simultaneous estimation of the regression target and the uncertainty bounds through two models. So here we have the network named F and I. So in the first model, we actually just predict the regression target. In the second model, we actually try to calibrate the intervals that are predicted by the first model. So the last function for my first model could be just like a heteroscedastic neural network model, which I discussed earlier, where we try to predict both the mean and the variance of the target value, which is assumed to follow a Gaussian distribution. Or it can be based on the quantile regression model, where I predict the mean value of the target and also some quantiles based on which my uncertainties can be estimated. So in the calibration, in the prediction interval calibration network, we come up with objectives such that the intervals or the uncertainty estimates produced by my primary network, which is the mean network, is well calibrated. And again, I use these well calibrated estimates as a feedback to my mean network or the primary network. So this way, there's a pseudo supervisory signal. We also show that the uncertainty estimates that we produce are meaningful by using these uncertainty estimates in the training procedure. So suppose we have a signal saying something is really off, my prediction is really off, and the uncertainties are large. So we try to incorporate that information while training my primary network such that the mean is adjusted accordingly. And most importantly, we make sure the predicted uncertainties are well calibrated. So my accuracy of the model is consistent with the uncertainties or inherent noise in the model or the data itself. And we also don't differentiate the uncertainty source here, so it's a black box approach. So we just give you a prediction, we just output prediction uncertainties or prediction intervals that gives me the total uncertainty, which is the uncertainty due to both model and the target. So again, this is a collaborative process because one process is helping the other. For instance, the second network is actually giving me well-calibrated uncertainty estimates to drive the first network, and the first network uncertainty estimates are used to produce my prediction intervals. And that was the objective that we used. So we posed a bi-level objective optimization problem. So where the parameters of both the models are updated simultaneously. And we actually studied several use cases, including time series experiments, regression experiments, and object localization experiments. So in object localization experiments, the green box around the object actually is the mean prediction, and the shaded area is the upper and the lower prediction intervals or the prediction uncertainties. So as you see, in some cases, the mean prediction is actually poor, but we are kind of compensating it with the shaded areas. That's the prediction uncertainties. And we also say it's calibrated. I mean, we also show that these intervals are well calibrated. Again, for the time series prediction, we actually come up with prediction intervals around the true target and check the calibration, meaning check how many true values are falling within our predicted interval. So in this
the previous slide, sorry, I had a question. Or when do you stop? How do you know when to stop?
Yeah, so it's an optimization question there. So in all these experiments, we observe that both the models converge at the same time, almost at the same time. So we just look at the convergence behavior and stop. We actually didn't have any issues when training these models. The reason why we think is the pseudo-supervisory signals from the calibrated network or the uncertainty estimates from the calibrated networks are meaningful. We're not just producing some random values. So since we are using that for training the mean or the primary network, we could show that the uncertainty estimates were good and we were able to regularize the process.
let's say I have already a pre-trained and I want to see how much uncertainty is there. So I can use that model this framework, right? And so how would the optimization strategy go?
So if you use a pre-trained network, there is no way to use the uncertainty estimates that you're getting. So in this process, we are actually driving the training process through uncertainty estimates that we get. So in the literature, what usually people do is just have a training model and then come up with some uncertainty estimation as a post hoc technique. So as you said, you can have a pre-trained network and use some post hoc strategies to come up with uncertainty estimations. But we propose this to be more useful because you're also using some knowledge in addition to your training data. And again, if you use pre-trained networks, you would require calibration data set. So you can't use the same training data set to obtain calibrated uncertainties estimates. But in this case, we even without additional calibration techniques, we were able to produce superior calibration and mean performance. So these are some of the use cases that we tried. So the other work was to use calibration as a learning objective. So in some strategies like heteroscedastic neural networks, so we actually assume the residual to follow some distributions. So we assume some Gaussian distributions on the target. But in some cases, we may not have information of how my residual is changing. So residual here means the difference between my true target and the value that the model is predicting. So in such cases, just placing some prior may not be very efficient. So you can, that was the motivation for this work. So we observed that calibration alone is sufficient to drive the learning process. So in the previous case, I commented that the calibrated uncertainty estimates were used to regularize the mean estimation process. But in this work, we actually showed that calibration alone is sufficient to drive the mean estimation in regression applications specifically. So usually any regression or a predictive modeling can be posed as the function there, where the second term is just a regularization term. In the first term, you have a fidelity metric, which is a function of the residual, which the difference between the true value and the value that the model is predicting. Suppose we assume the difference being symmetric, then we can assume a Gaussian distribution, and the loss function just becomes MSE term, that is y minus y hat the whole square plus some regularization term. So what if we have no clue about how these residuals are changing or what distributions these residuals are following? So in such cases, we actually showed calibration to be a good learning objective. So what we did was we came up with, again, two model structure. So the first model was just predicting my mean values, and the second model was predicting calibrated uncertainty estimates. But the objective for both the models was just calibration. I'm just not showing the loss functions because it's a little math intensive. So basically, I aim at achieving calibrated uncertainty estimates in both the cases. So in the second network, again, I achieve good calibration and use those calibrated intervals as my errors and use those errors to drive my learning process. And these were some of the empirical results, and we tried all this on standard UCI regression datasets, which is usually used in the literature. So we were able to show RMSE, or the root mean square error performance, was superior in almost all cases, and ECE is the usual calibration metric that is being used, which is expected calibration error. So people have so in ECE, what we do is for each confidence value, say from 0.1 to 0.99, we just compute how many true values lie within the given or within the estimated uncertainty interval. So that way, and we just average the error over all confidence values, and we plot those errors there. And again, we observe our uncertainty estimates are superior when compared to the existing strategies. We compare the existing strategies, namely dropout, complete dropout, Bayesian neural net, and stochastic neural network. And adding to the previous uncertainty estimation techniques, so in Monte Carlo dropout, we were supposed to pick the dropout probability, the probability with which we drop the units during the training and the test time. But in concrete dropout, the model itself is trained in such a way that the probabilities are selected based on the training data. So the other work was heteroscedastic calibration. So all these uncertainty estimators needed explicit calibration objectives, and we also there's been literature which shows that existing deep learning models are not well calibrated and hence not reliable, especially for critical applications. So in this technique, what we tried to answer was, can we just come up with inherently well calibrated uncertainty estimators? So just to avoid any post-hoc recalibration technique, recalibration strategies, or even to come. So for instance, you were talking about pre-trained models. So in pre-trained models, again, we need some post-hoc calibration technique, or you don't want to start the model training from scratch. And again, placing some explicit calibration objectives might be difficult when training bigger architectures. So in this technique, what we did was, given any, we made an interesting observation where a basic heteroscedastic neural network objective, an objective like this, was able to produce well-calibrated uncertainty estimates. So what we did was consider any kind of uncertainty estimates from the current techniques, like maybe dropout or decon symbols. So we just took estimates from existing strategies and used this kind of an objective for training the model. So, but the model is not optimized to produce sigma 0. So we have some external uncertainty source. So we take those while training the models and input that for the sigmas in this kind of a loss function, and we observe that the uncertainty estimates that we get are again well calibrated. The calibration errors were minimal, and also this helped to regularize the mean prediction because we have some kind of uncertainty information. Why not just use it while training the actual model? So this way, we were able to regularize the learning procedure and also to improve uncertainty calibration. So overall, in today's talk, we actually briefly went over the existing strategies, and since the main issue with uncertainty estimation strategies is you don't have ground truth. So only one way mostly people that mostly statistic literature has been using is calibration. That's why I focused a little more about calibration strategies at the end. And again, the other uncertainty evaluation strategies would be to actually use the uncertainties in applications when the models are deployed and see if the values predicted are reasonable or even able to explain the model behavior. And these are some of the key references. And if anybody has any questions.
Are uncertainty models more prone to underfitting since they deal more with trying to, expect to be wrong more of the time. If that makes sense.
The objective of including uncertainties in the model is to actually have some is to bring in that capability that model can express itself. So if you simply have some deterministic or point estimates, so the model is just giving you some predicted value. We have no idea whether it's good or bad. I mean, whether the prediction is accurate or not, right? By incorporating uncertainty estimation strategies, what we're trying to say is giving an extra dimension or giving an extra possibility for the model to express itself. So it doesn't have to do anything. I mean, it shouldn't affect your training process. Like it has nothing to do with whether the model is underfitting or overfitting. So suppose the model is underfitting. In that cases, I can expect the uncertainties to be very large. So that kind of indicates that your model is not doing good. So maybe you can include these. That's the reason. In the first technique, we kind of use those uncertainty values to actually guide the training process. So suppose my model is training, if I'm expecting the model to produce good quality good quality uncertainty estimates, I expect the uncertainty values to be large. So if I get large uncertainty values, and if there is a way to use those uncertainties while to correct my learning procedure, then I can avoid overfitting and underfitting.
So it's almost like a compensation for how the model's already made.
Yeah.
Okay,
Yeah,
cool.
exactly.
Oh, by the way, great presentation. So I have a question. So when this topic mentioned about predicting the uncertainties, that is a combination of both statistical and analytical. So are there any work that is being done to differentiate between the model explicitly say the statistical uncertainty and the analytical?
So it basically depends on what kind of objective I'm using. So in one of the work which I showed, I just mentioned it's a black box approach. So I'm not differentiating what uncertainties I'm trying to estimate. So I'm just coming up with prediction intervals or prediction uncertainties that are well calibrated and meaningful. So in the last case, again the second case was black box model. So I'm not differentiating what uncertainties my model is capturing. I'm just giving you some meaningful uncertainty estimates without differentiating whether it's from the data or from the model. But in the last case, I'm actually using uncertainty estimate from a source. Just suppose, say, I'm estimating uncertainties from dropout or Bayesian neural networks. So in that case, there is that characterization of uncertainty. So I'm just actually taking uncertainty from a source, trying to calibrate it, and trying to use that for my benefit. So yeah, it basically depends on what kind of objective you're training the model on.
Does any of your work involve real world data, or is this all just from published data sets?
It's mostly published data sets. We are working on some real world scientific data sets too.
In what domain?
It's basically a physics data set.
Thank you.
Awesome. Thank you so much, Bindya, for that one. I guess that will about wrap us out. Again, just to open the floor one more time, any announcements that anyone wants to make. Speaking Saturday, April 4th, both before speakers and attendees to that, right?
Close to speakers that we are, we officially open that up, but we are now just looking for people to show up at the event. Free, in university, well attended, we're going.
Yeah, lots of cool classes I've done before, so it's worth checking out if you haven't already. Anyone else want to do anything? Make any announcements? Any similar presentations they might be doing? We at Udestic are always looking for new talent, by the way, so especially cloud engineers. And I think we just had a senior data scientists would show up too. Am I wrong about that? Or?
You'll sort of have to look online to see when it's open and how the cause is kind of based on the forecast.
Gotcha.
Yeah.
They open and come and go, so keep your eye out for them. Maybe. But again, really any kind of technology prowess that you have, we'd love to see if we could get you on board with anything like that. So if that's something you're interested in, come talk to me and I'll get you talking with people that you're talking to. Again, for those who came in late, hopefully you got the message, but we are not validating for the garage across the way anymore, so hopefully we're able to grab one of these meeting spots, which go forward for free after 6, so we recommend it right there for future reference. I think there's some pizza left over, so please take another slice on your way out, so that way we can throw those out. Otherwise, you know, we have college students here, so they'll take it if you don't. And if that's all, then I think we're good to go. So thank you guys so much. We meet the last Wednesday of every month. So whatever the last Wednesday of March is, I think it's in 4 weeks, maybe 5, is when we meet again. Cool. So last Wednesday of each month, you should see the invite for that go up, hopefully 2 weeks out at the latest, if not earlier than that. So just keep your eye out for that meetup page. For these slides, we will be posting it on the YouTube channel. So if you guys don't know, we have a YouTube channel where you can check out the recordings of all these presentations and maybe hopefully you can get me a copy of the slide set too. Possible. So you guys can check out the slides, starting at the small screen for today. Otherwise, I'll let you guys get to it. So thank you guys so much for coming out again and have a good night. Yeah. You're on a whole other level with us. It's like, no, that's funny. It's like, you have this like second chance.